In this section, we're going to work on multiplying and dividing radicals. And our basic approach is just to use this fact that I can, we know that we can split up radicals over multiplication, but we can also combine them if they're the same index, right? So like that's an important note here. These are the same index or same order. So, we'll start out with a couple of simple ones. The square root of 5 times the square root of 2 is just the square root of 5 times 2, which is the square root of 10. You always want to make sure, if you're giving an answer of radicals, that you have a simplest radical form, that you give the result in a simplest radical form. The square root of 10 is already simplified. The cube root of 6 times the cube root of 4, we can combine that as the cube root of 6 times 4. Now, you might be compelled to say, okay, I'm going to multiply and that's a cube root of 24, but keep in mind you want to simplify, you want to make sure your radicals are in simplest form. So when you simplify a radical, it always begins by factoring. So rather than multiply that out, I'm actually just going to continue factoring. 6 is 2 times 3, 4 is 2 times 2, and it looks like now that we've multiplied them together, we do in fact have a set of 3 2's that we can take out, and what's left inside is a 3. 2 times the cube root of 3, and there's the product in simplest radical form. Let's do one more. These are two fifth roots, so I just do a quick check to make sure that the orders or the indices are the same of that radical. So they're both fifth roots, which means we can proceed by combining it under a single radical. And you'll note that there's no perfect fifth powers present in either of these two radicals, but when we combine them we might end up with perfect fifth powers. So I'm going to begin here. 8 is 2 cubed, and then I have a cubed b to the 4th. And then in the second radical, I've got another 8, so that's another 2 cubed, a squared, b cubed. Alright, I'm going to simplify this expression here. 2 cubed and 2 cubed. That's 2 to the 6, because we can add those exponents. A cubed and a squared is a to the 5th, b to the 4th times b cubed is b to the 7th. Now what I'm looking for here are perfect fifth powers. So now I'm going to rewrite this, I hope, in a helpful way. 2 to the 6th, I'm going to write that as 2 to the 5th times 2, and I have an a to the 5th. And b to the 7th I'll rewrite as b to the 5th times b squared. So now here's the things I can take out. So I have 2ab that I'm going to pull out of this radical times the fifth root of 2b squared. And that is as far as we can go on this one. Alright, so now we have some expressions that involve addition and subtraction. In part A here, I've got the square root of 2, and I'm multiplying it by 3 root 5 minus 4 root 2. We're going to proceed just by using the distributive property. So I've got root 2 times 3 root 5 minus root 2 times 4 root 2. And then I'm just going to simplify each of these individual products. So in the first product here, I've got root 2 times root 5, and that is the square root of 10. So I've got 3 square root of 10 minus. In the second product, I've got root 2 times root 2, which equals 2. There's no radical there, and then I'm going to multiply that by the 4 that's already there, so that's 8. And there is a simplest form of that expression. As always, we're going to be careful with addition and subtraction. We cannot distribute an exponent over addition. So 3 plus the square root of 5 all squared. Well, I'm going to just write out what this means. If I'm squaring something, I'm multiplying it by itself. So I've got 3 plus root 5 times 3 plus root 5. Now you could use FOIL, or I'm going to use the little grid here that we've used in the past to multiply things out. So across the top row, I've got 9, 3 root 5, 3 root 5 in the bottom row. Root 5 times root 5 is 5. So now we have like terms. In fact, we have like terms really on both diagonals. I've got my two constants here. That's 14. And then 3 root 5 plus 3 root 5 is 6 root 5. So this simplified result is 14 plus 6 times the square root of 5. In this example, now we're seeing a product. It looks pretty simple, but we should just note that we're multiplying two radicals of different index, right? So I've got a cube root times a square root. And when we're multiplying radicals with different index, I'm going to begin by writing each as a rational exponent. So the cube root of 2 is 2 to the 1/3 power. The square root of 5 is 5 to the 1/2 power. And if we want to be able to write this as a single radical, right, with just one index, that means I want to be able to write each of those exponents with a common denominator. So I'm going to take that 1/3, I've got a 1/3 and I've got a 1/2, so that common denominator is going to be 6. 2 to the 1/3 I'm going to write as 2 to the 2 over 6. 5 to the 1/2 I'm going to write as 5 to the 3 over 6. I'm choosing to do that because getting a common denominator is how I'm going to get a common radical. This is the same as 2 squared times 5 cubed all to the 1 over 6 power. And that 1 over 6 power is equivalent to a 6th root. 2 squared times 5 cubed, and 2 squared times 5 cubed is 4 times 125 is 500. Alright, now let's move on to dividing radicals. Our focus is on rationalizing the denominator. We already know how to do this in some instances, so we're going to begin with a familiar type of example, 1 over root 3. If I want to rationalize that denominator, I'm going to multiply by the square root of 3 on the top and the bottom. And we get the square root of 3 on top. On the bottom, root 3 times root 3 is 3, and that's as far as we go. If the denominator is just a single radical, this type of approach works really well. But if the denominator involves a sum or difference of radicals, we have to modify our technique a bit. In this next example, if I were to just multiply by the square root of 3 on the top and the bottom, it would not get rid of all the radicals. If I were to multiply by just the square root of 2, it would not get rid of all the radicals. You might think, oh, let me be clever, I'll multiply by root 3 times root 2, right, like the square root of 6. But that won't get rid of all the radicals either. So what we're going to do is multiply the top and the bottom by the conjugate of the denominator. So the conjugate is what you get when you change the sign in between. So here I'm subtracting them. I'm going to change that just to addition. And I'm going to multiply the top and the bottom by the square root of 3 plus the square root of 2. So let's see what happens. On top, obviously, I think we know what we get, right? It's just the square root of 3 plus the square root of 2. On the bottom, we need to find that product, so I'm going to set up my little grid here. Now across the top, root 3 times root 3 is 3. And root 3 times a negative root 2 is a negative root 6. Across the bottom, root 2 times root 3 is root 6. And root 2 times negative root 2 is negative 2. We have our like terms, so here are constants. The rational part, right? The part with no radicals, 3 minus 2 is equal to 1. And root 6 minus root 6, well, that's equal to 0. So this product is just equal to 1. And of course we would write this in a more simple way by just calling it root 3 plus root 2. Now you can convince yourself this is true. I chose a numerical example here because it's easy to see, to convince ourselves that we're right. In the calculator, I'll take 1 divided by, and then the square root of 3 minus the square root of 2. And there's that result. And then if I also find the square root of 3 plus, plus the square root of 2, we get the same result. So these are equivalent. Okay, so let's do another one. We need to rationalize this, and actually let me leave some space for what we're going to do. Our same technique will work. I've got the square root of 6 plus the square root of 2, so I'm going to multiply the top and the bottom by the conjugate of the denominator. So that I'm going to multiply by the square root of 6 minus the square root of 2. So now I've got some products to work out in the top and the bottom. So maybe I'll work on the top first. 3 root 6 negative root 2 root 6 negative root 2. So across the top, 3 root 6 times root 6 is going to be 3 times 6, or 18. Root 6 times a negative root 2 is a negative root 12. In the bottom row, 3 root 6 times a negative root 2 is a negative 3 root 12. And negative root 2 times negative root 2 is a positive 2. So we have along this diagonal a total of 20, and along this diagonal a total of negative 4 root 12. So 20 minus 4 root 12. Okay, in the bottom, that product, root 6 plus root 2 over root 6 minus root 2. Across the top, root 6 times root 6 is 6. Root 6 times root 2 is root 12. Across the bottom, negative root 2 times root 6 is negative root 12. Negative root 2 times root 2 is negative 2. So look, along this diagonal here, those cancel, right? Root 12 minus root 12 is 0. And then along this diagonal, 6 minus 2 is 4. So the denominator is 4. Now we can do some simplifying. We're not done yet. And there's 2 reasons that we're not done. One is that the square root of 12 here can be simplified. Okay, so the square root of 12, I'm going to come down here. The square root of 12 is 2 times 2 times 3 take out a pair of 2's, or I've got a pair of 2's, so I take out 1, 2, and then I'm just left with 3 inside. So this is equal to 2 root 3, so what we really have up here is 20 minus 4 times 2 root 3, that's 8 root 3 all over 4. So now we've simplified that radical. The next thing we need to do is make sure our fraction is reduced. And we have a common factor of 4 in the top and the bottom. So we could take out a 4 from the top. If I take out a 4, we have 5 minus 2 root 3. Now we can cancel the common factor of 4, leaving us with just a 1 in the bottom. So our final result is 5 minus 2 root 3. And if you like, you could pause now and kind of convince yourself that it's true. You could put this in the calculator, see what you get numerically, and compare that with what you get when you enter that into the calculator. Spoiler alert, they're the same thing.